Hello. For this video, we will be discussing doing sensitivity analysis on linear programming models. What is sensitivity analysis, or how do we do sensitivity analysis? We do sensitivity analysis by asking questions such as what will happen if additional supply comes in, or what if you forgot to take into consideration another constraint, or what if your coefficients either in the objective function or in the constraints change. So so essentially what we're dealing with right now are changes in your linear programming model. For our purpose, for our class, we will be focusing on a very particular aspect of sensitivity analysis, and in this case we will be dealing with changes in the right hand side of our constraints. So essentially, what we will be discussing are things that will happen to your model if and when the right hand side of your constraints change. So for this example, we will be discussing again the red blue gadget problem with this linear programming model. Okay? And because we're dealing with changes in the right hand side, then we will be talking about changes to 1000, 1200, and 1800. Okay? And for this video, we will be um, particularly talking about changes in the steel constraint. So the first constraint, 2x1 less than or equal to 1000. I will leave it up to you to determine the changes that will happen for the wood constraint and the labor constraint. Okay? Okay. Now, before we go on to the subject matter, I will be posing two questions that we will be answering. The first question is, let's say a salesperson goes to you and offers to sell you additional steel. So this person might be someone from a hardware store uh, producing steel, no? And let's say he goes to you and offers you additional steel. So the question that we have to answer right now is, how much are you willing to purchase additional steel? So let's say if the salesperson offers you additional steel for, let's say, 20 pesos per unit, will you purchase the additional steel? What if it's 21, 22? What if it's 30? So the question that we need to answer is, how much are you willing to purchase? For how much are you willing to purchase additional steel? And let's say the price that was given to you by this salesperson is favorable. How many units of steel are you willing to purchase? Okay, so that's the first question that we will be answering. The second question that we will be answering eventually is in a different point of view. What if, instead of someone going to you offering you additional steel, what if this person who went to you is offering to buy or purchase your steel? So instead of you producing red and blue gadgets using these steel units, what if this person offers to buy your steel? So the question is, for how much per unit are you willing to sell your steel? And in this case, given that the price is favorable, how many units of steel are you willing to sell for this price? Okay, so what I have here is the graphical solution to the red blue gadget problem. So we have the x-axis and the y-axis. Okay, and we have the first constraint, 2x1 less than or equal to 1000. So this is at x1 equals 500. This one is your 2x2 less than or equal to 12. This is at x2 equals 600. And finally, we have our 3x1 plus 2x2 less than or equal to 1800. Okay? And using the graphical solution, we will be able to determine that this corner point, which has a solution x1 equals 500 and x2 equals 150 and a z of 295,000 as our optimal solution. Okay? So now, to answer the first question, which is what if someone is trying to sell you additional steel? How do we know how much we are willing to purchase additional steel? In order to know, in order to answer that question, we need first to know what is the effect of adding additional steel to your supply, and what is the effect eventually to your optimal solution. If you're adding your if you're adding steel to your steel supply, then if we go to this to the linear programming model, you will see that this 1000 on the right hand side will go up. Okay, so you have a 2x1 plus 0x2 less than or equal to 1000, but this one will go up. Okay, now given that the right hand side will go up, what is the effect on the graph? The effect is that this vertical line, which represents your 2x1 less than or equal to 1000, will shift to the right. Okay, and let's say your 1000 we increase by, let's say, 100, and therefore this becomes 1100. What will happen? What will happen is what will happen is this line, this vertical line, will shift to this line. Okay, how do I know that this will shift to this line? Because I will this point is an x1 equals 550, and as you can see, that is the x1 intercept of this constraint, no? So if you divide everything by 2, you get an x1 less than or equal to 1100. And because this line shifted to this line, then your original optimal solution actually moved. No? How did it move? It moved to this corner point. And what is this solution? This solution is an x1 equals 550, an x2 equals 75, and a z of 297,500. Okay, again, from this optimal solution, it moved down to this corner point. Why? Because as you can see, uh, from this original feasible region, okay, we are technically adding this feasible region because we are increasing our right hand side from 1000 to 1100. Okay, and as you can see, if you compare the z value of the new optimal solution, which is 297,500 versus the original one, which is, I'm sorry, versus the original one, that is 295,000. And as you can see, if you compare the new z value given given that we increased our right hand side from 1000 to 1100, the new z value, so z of new is equal to 297,500, and your original z is 295,000 is 295,000. Okay? Therefore, what we get if you subtract is a change in z equals to 2,500. And this 2,500 change in z was brought about by a change in steel of 100 units. Okay? Why? Because your steel new equals 1,100 and your steel old is 1,000. And therefore your change in steel is 100. And if you get the ratio of the two, you get a value of 25 pesos per unit of steel. So what is this 25 pesos? This 25 pesos tells us that for every unit of steel that you increase from 1,000 up to 1,100, you will be getting an additional profit of 25 pesos per unit. Okay? And we've done that from 1,000 until 1,100. So for now, what I'd like you to do is I'd like you to remember this change in z over change in steel that is equal to 25. Okay? And that is from 1,000 to 1,100, which is an increase of 100. Okay? Now, what I want to do next is, what I'd like to do next is to further increase our steel. Instead of just increasing by 100, what if we will increase this up to 200? Some arbitrary value, let's say 200. Okay? So in this case, we cross this out and we increase by 200. Now, if we increase the right-hand side by 200, what will happen to the graph? The graph will, this vertical line, no, will move to this line, touching this corner point where the diagonal line, this diagonal line, touches the x-axis. Okay? And in this case, if we compute for this corner point, let me use red. This corner point is an x1 equals 600 and an x2 equals 0 and a z of 300,000. Again, what will happen is because you are increasing your steel by from 1,000 to 1,200, you're actually adding feasible region. And what feasible region did you just add? Technically, you're adding this part, and that is why from your original corner point, this corner point, it actually moved to this corner point with a solution x1 equals 600, x2 equals 0, and z equals 300,000. And doing the same analysis a while ago, if you get your new z, which is 300,000, and your original z, which is 295,000, And if you get your steel new, which is 1,200, and your original steel, which is 1,000, what you will get is a change in Z, which is equal to 5,000. Why 5,000? Because that's 300,000 minus 295,000. A change in steel, which is equal to 200. And therefore, if you get the ratio, you still get a ratio of 25 pesos per unit of steel, which supports our ratio that we got a while ago. Which means this 25 pesos is effective not only plus 100, no, not only plus 100, but actually plus 200. What we don't know is what if we go beyond 200, and that is what we will answer next. Okay? Okay. So given that we found the effect of increasing your steel, sorry, the effect of increasing steel in your model increases your Z by 25. What we will do now is to answer the question: what if this increase in Z is beyond an additional 200? Okay. Now, let me superimpose this part of the graph. What will happen is this is your x-axis and this is your diagonal line. Okay, and at a right hand side of 1,200, the vertical line is already here. Okay, and that's why you have your optimal solution here. Now, if we increase our steel supply by more than 200, okay, what will actually happen is this vertical line will move further to the right. No? And we don't, well, it depends on how much you increase beyond 1,000, beyond 200, then there is a corresponding shift to the right of this line, no, of this line. Okay. However, I'd like to point out that if we shift this line to this line, then we are not changing the feasible region, because if you remember the feasible region, let me shade the feasible region. This is our feasible region, well, including the left part now, because this is just the zoomed in part of this area, but technically the feasible region is everything here. Okay, everything that is red. Okay, now if we increase the right hand side beyond 200, then what will happen is this line will shift to the right. However, even if this line shifts to the right, your feasible region, this feasible region, will not change. Not change. And because your feasible region will not change, then if you if we treat this as our original z value, our original solution, which has a z value of 300,000, okay, and the amount of steel is equal to 1,200, and if we further move this vertical line to the right, or increase this by more than 200, then your new z will still be equal to 300,000. Why? Because your feasible region will not change, and therefore your optimal corner point will still be at this corner point. And because your new Z is still 300,000, and let's say your steel is some value, some X that is greater than 1,200, if we get the ratio that we were computing a while ago, this ratio, no? So if we get the change in steel, Z, sorry, the change in Z is 300,000 minus 300,000. The change in steel is, well, in this case, some value X minus 1,200. And in this case, X is something greater than 1,200. Therefore, if we divide everything, if we divide the two, then we get a value that is equal to 0. So what does that mean? What does that mean? That means the ratio that we got a while ago, this 25, is only effective until an increase of 200. Because moving beyond 200, the ratio now becomes 0. Now, how do we explain this intuitively using the graph? Using the model, sorry. So going back to the model, if we increase this 1,000 up to 1,200, what will happen is there will be some reallocation of the labor unit. Instead of producing 150 blue gadgets, it will decide to reduce the production of blue gadgets and move all the labor units to the production of red. And that is why, if you remember, at this point, the solution is an x1 equals 600 and an x2 equals 0. So from an original x1 equals 500 and an x2 equals 150, what happened was the company decided to not produce blue gadgets anymore. That's why from 150 it became 0. And from the reduction of blue gadgets, from the reduction of the production of blue gadgets, you were able to free up some labor hours, and in that case you were able to produce more red gadgets because you have additional steel, and that is why your steel production increased from 500 to 600. However, at this point, you can no longer reduce your production of blue gadgets because it's already 0, and therefore no matter how many increase in steel you add here, no, or you do here, it will not affect the model anymore, and that is why the ratio is equal to 0. There is a nice intuitive way in which we can explain the change in Z over change in steel value of 25. Remember, in our original optimal solution, our solution is an x1 equals 500 and an x2 equals 150 and a Z of 295,000. And then what happened was when we increase the steel by 200, no, we get a new optimal solution of x1 equals 600 and x2 equals 0 and a Z of 300,000. So what happened here was there was a reduction of 150 units of the production in blue. And because there was a reduction of 150 units um, of blue gadget, then we can expect our profit to be reduced by, well, in this case, 45,000. Okay, negative. However, however, in this case, because there was an increase of 100 in the production of of red gadget, then there is a positive increase of 50,000. And that is where you got the net increase of 5,000 in Z, which relates to the increase of steel by 200, which equates to a 25 change in Z over change in steel. Another thing to note um, in the previous analysis that we did was that given the original optimal solution at this corner point, because we are shifting this constraint to the right, therefore, as we shift this line to the right, you should notice that this optimal solution actually is running, in quotation marks, running or moving along this line. And this tells us that if we shift this vertical line up until this point where it touches this corner, then we know that in this particular range, no, or shift from this vertical line to this vertical line, we can observe that the change in Z over the change in steel will always be 25. If you remember in the previous discussion, anything beyond this, the change in Z over change in steel is already 0. But within this area or region, we know that the change in Z over change in steel is always 25. And I think we can do that same analysis when we try to reduce our steel units. And this is where we will be answering the second part of our question. And that question being, if a person goes to you and offers to buy your steel, for how much per unit are you willing to sell? And how many units of steel are you willing to sell? In this case, when you are willing to sell your steel units from an original vertical line here, and because you are reducing your steel units, you're actually shifting this to the left. And because you are shifting this line to the left, then you should expect your optimal solution to be, in quotation marks, moving or running along this line. And because the optimal solution is moving along this line, then you should expect that at this point, at this corner point, where this vertical line shifted to this vertical line, or in this case, the range covered by this move, no, from the original to the eventual reduction of steel, you can expect the change in Z to be over change in steel to be of the same value, whatever that value is. Okay, and in this case, this is where we will be computing for this change in Z over change in steel. So how do we now compute for this change in Z over change in steel for this range? For this range, what do we do? In order to compute the change in Z over change in steel, we first need the original optimal solution. So x1 is 500, x2 is 150, and a Z of 295,000. On the other hand, if we shift this vertical line to the left, and let's say up until this point, we will actually get a new optimal solution. X1 equals 200, x2 equals 600, and a Z of 280,000. So your new Z equals 280,000. Your old Z is 295,000, if you get the change in Z, you get a change in Z of negative 15,000. Your new steel is equal to 400, and I'll tell you later why this is 400. Your old steel is 1,000, and therefore your change in steel equals negative 600. And if you divide the two, your change in Z over change in steel is still 25. So this one is still 25. And how do we know that the reduction in steel from this to this is a negative 600? How do we know? Because your x1, here, because your x1 is equal to 200 and x2 equals 600, if you plug in x1 equals 200 in this linear programming model, in this constraint, so 2 times 200, this equates to 400. And because this is 400, we can actually reduce this 1,000 down by 600 or up down to a value of, or a right hand side of 400. That means the shift from this line to this line is actually a reduction in steel by 600. So in summary, as you can see, in summary, let me erase. In summary, we can say that from this range, from this vertical line on the left until this vertical line on the right, the change in Z over change in steel is equal to 25, and we can allow a reduction of steel by equals 600, because from a steel of 1,000, from a steel of 1,000, your steel here becomes 400. So it's a reduction, allowable reduction of steel by 600. And this increase at this vertical line, your steel is equal to 1,200, which means you are allowing an increase in steel by 200. And therefore, given this output, we are now able to answer the two questions we posted a while ago. Again, reading the two questions. If a salesperson goes to you and offers to sell you additional steel, for how much per unit are you willing to purchase additional steel, and how many units are you willing to purchase? So in this case, you are willing to purchase additional steel if additional steel will only cost you at most or at a maximum 25. So you are willing to purchase additional steel at the highest price of 25. But you are only willing to purchase 200 additional steel, because this change in Z over change in steel of 25 is only effective up to a positive or plus 200 units in steel. And in the same manner, if you're willing to sell, you are willing to sell your steel units for at least 25. Why? Because for every steel unit you are going to sell, so in that case, it's a movement from this line to this line, or a movement to the left, then your Z will change by 25. No? Because you're selling steel, your Z will go down by 25. So in order for you to be to be willing to sell your steel, then you should be selling it for at least 25 pesos per unit.